So let's begin. Hello everyone, I am Srishi Siddharth. I am a PhD student associated with the Center for Systems and Control at IIT Bombay. And I'm also a TA for this course, WE46 Theory and Dynamical Systems. So welcome to 7th week tutorial session. Let's so let's start with a review of the topics that we are going to discuss. Start with tests for observability and detectability. Then we'll also discuss the standard form for an observable system. Standard form. Also talk about minimal realizations. Talk about karma decomposition. So let's begin with a few questions on observability and detectability. First question is a simple one. Determine the observability of the LTI systems described by the following matrices. For part A, the A matrix is 0, 1, 0, 0, and C is 1, 0. So for observability, we just need A and C. We don't need the matrix B or T. So we also have a second part. A again is 0, 1, 0, 0. But now C is changed to 0, 1. That is where considering the output as a second string. Alright. So let's begin. We had 3 tests for observability for an LTI system. So let me just write them down first. So the LTI system is observable, or the pair CA is observable. First part, rank of the observability matrix is equal to F. Second, no eigenvector of A is in the kernel of C. This means that if V is an eigenvector, then CV is non-zero. Third is the PBH test. States that the rank of the matrix A minus lambda I C equals N, for all eigenvalues which are complex. So recall that for controllability, we arrange the matrices in group, right? So for controllability, we had rank of A minus lambda I B. And for observability, we are looking at transposes. So first of all, the row becomes two columns, A minus lambda I, and the second one becomes C because we're talking about observability. All right. So the simplest test for this second order systems in both the cases is to form the observability matrix. So let's do that. The observability matrix is going to be, again, it's going to be arranged in rows now. So it's going to be C, CA, and that's it because n equals 2. So it goes to CA to the power n minus 1. Alright, so for us, CA is 1, 0, 0, 1, 0, 0. So it's 0, 1. The observability matrix is 1, 0, 0, 1, which is identity. And of course, it is full rank. The determinant is 1. Therefore, rank is 2. This implies that the pair CA is observable. We have the second part. If we take second state as the output, does the system remain observable or not? So again, we have to compute CA. This time it's going to be 0, 1. Okay, so 0, 1, 0, 0. So this is the observability matrix. In this case becomes C, 0, 0. Okay, so you can see that there is only one linearly independent column or maybe just one linearly independent row. Therefore, the rank of the observability matrix is 1, which is not equal to n, which implies that the pair CA is not observable if we consider the second state as the output. If you have any doubts, you can just ask me. Also look at the other tests, maybe for example for part A, by computing the eigenvectors of A and checking if they lie in the kernel of C or not. So you can do that as well. For that we first need the eigenvalues of A, and so we have to determine the characteristic equation. That is determinant of A minus lambda I equals 0. Now we have the A matrix as, so minus lambda 1 0 would be equal to 0, which implies that lambda square equals 0. We have repeated eigenvalues at 0. Okay. So the eigenvectors for this case would be just A minus lambda I applied to some B equals 0. So we have 0, 1, 0, 0. 1 V2 equals 0, 0. We have just one equation, which is V2 equals 0. So, and V1 can be any scalar. So eigenvector can be, for example, A is 0, where A is some real number. Now let's see if what kind of vectors lie in the kernel of C. So kernel of C are all, let's say, X, let's start to such that C axis 0. Okay, so C for the first case was just first output, so 1, 0, x1, x2 equals 0, which is just one equation, x1 equals 0. So vectors in kernel of C are going to be of the form 0 and let's say B, where B is some real number. So you can see that this is completely different than the eigenvectors of A. Therefore, there can be no eigenvector of A which lies in the kernel of C. Therefore, the pair C is observable. Alright. Which implies that the pair C is observable. I hope this question was clear to you. Now let's move on to the next one. We have a third order system. Consider the matrices. It's 3, 0, 0, 5, 0, minus 1, 4, minus 1, 0. C equals 1, minus 1, 1. So the first part is the pair CA observable? Second part is show that the pair CA detected. Okay, so again we have three tests out of which we will compute the observability matrix. So answer A for n equals 3. This is going to be O arranged in rows. So C, C8, C is 2. Now let's compute CA first. This one 1, 3, 0, 0, 5, 0, minus 1, 4, minus 1, 0. This becomes 3 minus 5 plus 4, then minus 1, then plus 1. This minus 2 plus 4 minus 1, 1. Then we need CA square, which is nothing but CA times 8. 3, 0, 0, 5, 0, minus 1, 4, minus 1, 0. Okay, so we have 6 minus 5 plus 4 minus 1 plus 1. 5 minus 1, 1. Alright, so let's arrange them. O is 1 minus 1, 1. 5 minus 1, 1. So to determine the rank, you can either calculate the determinant or you can observe that these two rows are linearly dependent, sorry, columns. So for example, this is column 1, column 2, column 3. So you can see that column 2 is minus 1 times column 3, right? So the rank is already not 3. What we can just quickly calculate also is the determinant. This is 1 minus 1 plus 0 plus 1, 2 minus 5 plus 1 minus 2 plus 5. This is 0. So this implies that the rank of observability matrix is not 3, it's 2 values. So therefore, the pair C is not observable. Now let's talk about detectability. So before that, let's recall the PPH test for detectability. So we have A and C, and we know the PPH test, right? For observability, it is A minus lambda I. C should be equal to N. But for detectability, we are going to consider eigenvalues, such those eigenvalues, whose real part is greater than 0. So real part of lambda is greater than 0. Equal to 0. Alright. So we first have to determine the eigenvalues, okay? So let's find the characteristic equation. Lambda I is 3 minus lambda, minus lambda, and minus lambda. So the entries remain same. So we have minus 1, 5, and 4. Alright, so this is easy. We just have to expand around the first quotation. 3 minus lambda, then lambda square minus 1. 0. So we have lambda equals 3 equals lambda square is 1. Simplifies lambda is plus minus 1. So we have to test for two eigenvalues, lambda equals 3 and lambda equals 1. So let's start. For lambda equals 1, A minus lambda I becomes 2 plus 1, 0, 0, minus 1, minus 1, 5, 4. Of A minus lambda I, C as the last row. So C is 1 minus 1, 1. This is a 4 by 3 matrix. We cannot calculate the determinants. So let's see. So rank is going to be either 3 or less than 3. So see if the 3 columns are linearly independent or not. And C2, C3. Alpha 1 C1 plus alpha 2 C2 plus alpha 3 is 3.0. Or we have 2, 5, 4, 1. 0, -1, -1, 1. So we have the first equation, 2 alpha 1 plus 0 alpha 2 plus 0 alpha 3 equals 0, which simply implies alpha 1 is 0. Now we'll have to find out two equations in alpha 2 and alpha 3. So the first one is minus alpha 2 minus alpha 3 equals 0. This is 1. And then let's go to the last row. Minus alpha 2 plus alpha 3 equals 0. So this simply implies alpha 2 equals alpha 3. You can substitute in here to find that both of these are 0 as well. So rank is 3. So we have other eigenvalues here. Lambda equals 3. 3 a minus 3I is 0 minus 3 minus 3 0 0 minus 1 5. So we have rank of 1 1. You can actually see that this is a row of zeros. So there would be at most 3 independent rows, but let's find out if the columns are linear independent. That would be easy. We can just figure out by rows as well. So let's see. 1 5 4 1 plus alpha 2 minus 3 minus 1 minus 1. You can just omit the row of zeros plus alpha 3 minus 1 minus 3 1. Next equation is 5 alpha 1 minus 3 alpha 2 minus alpha 3 equals 0. Alpha 1 minus alpha 2 minus 3 alpha 3 equals 0. This implies that alpha 2 is alpha 1 plus alpha 3. We can substitute in these two equations. So we get alpha 1 minus 3 alpha 1 minus 3 alpha 3 alpha 1 is 4 alpha 1 minus 3 alpha 3. So we have this and this. We can just subtract these two. So there is 3 alpha 1 minus 4 alpha 3 equals 0. Alpha 1 equals 0. Then we can substitute again in any of these equations. Find that alpha 3 is 0, which implies that this is 0 as well. So for the two positive eigenvalues, lambda equals 3 and lambda equals 1, we have rank equals 3, which is besides the n. Therefore, the pair C is detectable. Alright, so I hope this question is clear to you. I'll wait for some time if you have any questions. If not, let's move on to the next question. Yes. So consider the following system. So equals 1 0 0 0 0 0 0 0 minus 1 times x. The output as well. So C1, C2, C3 times x. Here C1, C2, C3 are some unknown tables. So we have done a similar problem for the case of controllability as well. So these are some unknown tables. So part A is for which the system is observable. Provide an example. For C1, C2, and C3, for which the system is observable. Finally, provide a necessary and sufficient condition. C1, C2, and C3, so that the system is observable. Alright, so we Determine the values of C1, C2, C3 by the observability matrix test. So let's begin. Given the third order system, so the observability matrix is going to be A, CA, CSP. So CA is C1, C2, C3, and 1 is equal to 0, 0, 0, minus 1. This is C1, 0, minus C2. Then CA square is C1, 0, minus C3. Then 1, 0, 0, 0, 0, minus 1. This is then C1, 0, this becomes plus C3. Alright, so we have the first, let's form the observability matrix first. We have C1, C2, C3, C1, 0, minus C3, C1, 0, plus C3. So first that is determine the values under which the pair CA is not observable. So let's see. There are three columns. Okay. I can just write this column 1, column 2, so not 2 confused with the coefficients C1, C2, C3. This is column 3. Okay, so the first thing to observe is that C2 should be non-zero, because if C2 was 0, then this whole column would become 0 and there would only be two linearly independent columns. So the first one is that C2 should be non-zero. Sorry, we are talking about unobservability, so C2 should be 0 so that at least one column gets eliminated. So we need to find values of C1 and C3 as well. So if we put simply C1 equals 0, 0, then the observability matrix would just be the 0 matrix. Then the pair CA would be 0. Of course, this is just one value of C1 and C3. You can also choose some other values to show that under those conditions, under those values of C1, C2, and C3, the pair C is not observable. So this is just one example. So try some others. Okay. So in the next part, if we have to talk about the conditions under which the pair is observable. So we have C1, 0, minus C3. As an example, again, C2 should be non-zero so that this row is linearly independent from the others. Then we can have, let's say, C1 equals 1 and C3 equals maybe 1. So let's find out if the observability matrix is full rank or not. So 1 minus 1 now. So let's see, the determinant is 0, then we have -1 and +1, +1 and 0. So we have -2. So for this pair, or sorry, this triplet 1, 1, 1 implies that the pair CA is observable. There are infinitely many combinations of C1, C2, C3, which would give determinant non-zero, so you can try others out as well. But we just have to provide one example under which the pair CA is observable. This part is to provide a necessary and sufficient condition for C1, C2, and C3 so that the system is observable. So recall the three tests for observability. One was the observability matrix test, the other one was the PBH test, and the last one was the eigenvector test. And the eigenvector test actually provides a necessary and sufficient condition that there should be no eigenvector of A which lies in the kernel of C. So to do that, we first have to find the eigenvectors and therefore the eigenvalues of A. So let's start. Determinant of A minus lambda I equals 0. So A is one minus lambda minus lambda minus 1 minus lambda, and zeros everywhere else. So this is easy to solve now because this is just a diagonal matrix. The eigenvalues are, or the characteristic equation is simply this. So this implies lambda equals 1. Sorry. This implies lambda equals 0. This implies lambda equals -1. Now we need to find the eigenvectors associated with each eigenvalue. Let's quickly compute this. We have for lambda equals 0, A minus lambda I equals 0, which is AB equals 0. So we have 1, 0, 0, 0, 0, 0, -1, 1, V2, V3. So first is V1 equals 0, last is V3 equals 0, V2 can be any real number. So the eigenvector is 0, 0, and let's say some constant. So let's check, does this lie in the kernel of C? So how do you check that? We have C1, C2, C3, 0, A, 0. Simply implies that C2 times A. Okay. So we want the system to be observable. So this eigenvector should not lie in the kernel of C. Therefore, this should be non-zero. This should be non-zero for any real number A. So what does this imply? That C2 itself should be non-zero. Okay. So we have two more eigenvalues. We'll get the conditions on C1 and C3 as well. So let's do that quickly. 1. We have A minus I. So it will be 1 minus 1, 0. Then -1, -1, -1. And then zeros everywhere else. V1, V2, V3. So we have V2 equals 0, V3 equals 0. V1 can be in a scalar. So we have A 0 0. So we want this to be non-zero for any real number A, which simply implies that C1 should be non-zero. Finally, let's do this for lambda equals -1. So we have A minus lambda I, so we have A plus I. So 2, 1, and 0. So I just check what E is. That's 7. This plus identity is simply 2, 0, 0. So 2, 1, 0. And then zeros through. So we have the first equation V1 0, then V2 0, V3 can be any real number. Okay, so we want C1, C2, C3 applied to 0, 0, A should be non-zero for any real number. For the necessary and sufficient condition for observability is constants should be non-zero. Hope this question was clear to you. Now, let's move on to the next question. This is question 4. So we have to find the standard form of an observable system. A system described by the following matrices. Described by the following matrices. So we have A equals -2, 3, 0, 4. You just need A and C for observability and an observability level. So C is 0, 5. We all what the standard form looks like. So I'm going to write that down as A bar, which is 0, 0, 7. Mhm. 8, 2, 1. And again, the unobservable A. C can also be written as C 0, 0. This is decomposed into the observable part and the zero vector in general. And the pair A C0 A0 is observable. So if we have to transform into the standard form, we need a transformation matrix T. T is found by the by using the observability matrix. So let's first find that out. So C, C, D. See that the pair CA is not observable. Right? We need to transform it into the standard form for unobservable systems. Okay. So the transformation matrix T will have two. Okay, so we have two states. So transformation matrix T is going to be 2 by 2 because we need it to be invertible. So what we do is we pick out linearly independent columns from the observability matrix. So in this case, we just have 1, 4. So we write this down. And to complete the matrix, let's say that we choose some other linearly independent column, let's say 0, 1. So does T inverse exist? We can just calculate determinant of T to find out if it's invertible or not. This is 1, therefore T is invertible. This is the transformation. Then A bar is going to be, so T inverse AT. C bar is going to be C2. X bar, the new coordinates or the new states equals T inverse times X. Okay, so let's find what is A bar and C bar and see if we get the standard form. So T inverse is 1 upon determinant of A, and then we swap these two and reverse these signs. This -2, 3, 0, 4. Correct this quickly. -2. That is this comes out to be 10, 3, -24, -7. Okay, observe that the standard form has 0 here, which we do not have. Therefore, we'll have to select a different transformation matrix. You already have one column from the observability matrix. So we'll guess the matrix T again. We have 1, 4. And let's say we have something 2, 0. The determinant is still 1. So T is invertible. Now let's find out what A bar is. So we have 1, 0, -4, -2. Sorry, the determinant is -8. Yeah. Okay, so we have to divide by 1 by 8. So this is 1 by 8 -2. Then we have 3 minus 8. We have 8 here. And then -12. 2, 4, 0. So we can calculate this and then we write down the matrix directly. So this is 4, 0, 3, -2. Okay, so let's recall the standard form, that is the observable part, 0 unobservable part, and something data part. Okay, so this matches this. So we have found out the standard form for A bar. Then we have C bar equals, which is C0, 0, which is CP. So C was 0, 1. P is 0. This is 4 and this is 0. So this is C0. So we can see that for our case, we have a simple system where A0, C0 is 4, 4. So this pair is observable. So you can just check for scalars, right? For this case, n equals 1. So observability matrix is going to be n minus 1, I guess. C0. Observable. Therefore, we have transformed the system into the standard form for an observable system. Questions you can ask me. Meanwhile, I'm going to write down the next question. So find the variable economical form. Of the system described by the following transfer function. G hat of s equals s squared plus 6s plus 8. Here is q plus 9s squared plus 23s plus. Just a second. Alright. So we have G hat of s. So you can observe that this is a strictly proper transfer function. Call the controllable canonical form, and from the CCF form, we can get the observable canonical form or OCF. So we have controllable canonical form. Which means that we have a chain of indicators, and in the last row, we have the coefficients of the denominator of G hat of s. So in that case, we have ACCL equals, let's say we have a third order system here. Firstly, the highest order of S in the denominator is 3. Okay, so we have 0, 1, 0, 0, 0, 1. Minus alpha 1, minus alpha 2, minus alpha 3. Where the coefficients are taken in this direction. Minus 15, minus 22, minus 23, minus 9. Then we have VCCF, in which we just have the input present in the last dynamic. So we have 0, 0, 1. And then CCCF are some betas. So for third order system, we have beta 1, beta 2, beta 3. These correspond to the numerator of the transfer function. So I'm going to write down the general form for G hat, which I'm talking about. Beta 1 square plus beta 2s plus beta 3 cubed plus alpha 3s square plus alpha 2s plus alpha 1. Sorry, I have to write that down. So alpha 1, alpha 2 plus alpha 3. Okay. Now, once we have the CCF form, we can get the OCF form very easily. So note that the observable canonical form is the dual of CCF. So what does this mean? So we have the three matrices ACCF, ACCF, CCCF. In the A matrix, in observable canonical form is A transpose CCF, COCF is B transpose CCF. Right. Yes. And B is CCCF transpose. Or so we have our transfer function. So we know what betas and alphas are. So I'm going to write down ACCF as chain of integrators 0, 1, 0, 0, 0, 1. Then minus 15. Sorry, minus. Okay, so we have 9, 23, 15. This implies that VOCF is CCF as 0, 0, 1, which implies that COCF is CCCF is beta 1, beta 2, beta 3. We have 1, 6, 8. There's VOCF is 1, 6, 8. So actually you can check in one of the textbooks if the standard form is correct or not. You can easily figure out by this duality relation the matrices in the observable canonical form. Alright. So if this question was clear to you, we have found out the observable canonical form and the transfer function of the system was given. Question 6. We have to check if the state space model is a minimal realization. So x dot equals 1241 x plus 10b. The output is the second state. So when is the system represented in its minimal realization? So the given realization is minimal. So if it is both controllable and observable. It's simple, right? If we have been given that this realization is minimal, we have to verify this by checking the controllability, the rank of controllability and observability matrices. So let's quickly check these. So the controllability matrix C is B and AB. Of course, n equals 2. So AB is 1, 2, 0. So this means we have 1 and 4. Plus 1, 0, 1, 4. Then easily check that the determinant is non-zero. Therefore, the pair AB is controllable. Let's check the observability matrix where C, CK. It's going to be 0, 1, 1, 2, 4, 1. It is simply the second row. Observability matrix is 0, 1, 4, 1. So determinant is simply -4, which implies that the pair C is observable. These observations imply that the state space model is a minimal realization. Minimal realization of the system. Alright. So I'm going to wait for a few seconds before we move on to the next question. Let me know if you have any doubts. Okay, if not, let's move on to the next question. So consider the FBI system. Following matrices described by the so A equals 0 minus 1 1 1 minus 2 1 0 1 minus 1. B equals 1 0 1 1 1 2. C is 0 1 1. So determine the controllable, uncontrollable, observable, and unobservable eigenvalues. So for this, we will consider the Kalman decomposition of the system. So let's recall that. So we will recall Kalman decomposition. Simply transform the system into the standard form for uncontrollable system, standard form for an observable system, and then form the matrices, Kalman matrix. So I'm going to write the matrix down directly. Let's say that big matrix is A bar. First one is ACO, 0, and 0. ACX, ACO bar. This is 0, 0, 0, 0. So you can refer to the lecture slides to recall this. This is A. Similarly, we have the B and C matrices as well. So you can see that this is multiplied by in the differential equation by XC0, XC bar, XC bar O, and XC bar O bar. So O bar means that the system is unobservable, C bar means that the system is uncontrollable. So XC0 is both controllable and observable. There are states which are both controllable and observable. State which is controllable but not observable. We have the state which is not controllable but observable. States which are neither controllable nor observable. Have the same subscript in various values or of this matrix A bar. So here we have transformed the system given by the ABC matrices in the form A bar, B bar, C bar, where A bar looks like this. So I'm going to write down A bar directly. Let me just write that down. Just a second. The screen is not working. Meanwhile, if you have any doubts, you can ask me. I'm just going to open the screen again. Alright, so it's not working out. Let me just write this down. So let's say that we have transformed the system into some A bar, which looks like this. So I can just write down. The controllable eigenvalues are going to be the eigenvalues of ACO bar. So just say that controllable eigenvalues would correspond to CO bar. Uncontrollable eigenvalues would be of A C bar O and A C bar over. Observable eigenvalues, which will be determined by observable eigenvalues would be we have AC bar and AC bar over. Then we have observable and controllable eigenvalue would be by ACO. Alright, so I hope we can solve this question by reviewing the concept of Kalman decomposition. Now let's move on to the last question of this tutorial. Question 8 is to find a minimal state space realization of the following. Transfer function matrix. G hat of S equals 2S plus 1 upon S plus 1 and S plus 2 upon S plus 1. So the first step is to convert to the CCF form. Let's see. Alright, so let's see. We have to compute first D, which is extending to infinity. G hat of S. So this is nothing but, let's write this down. 2 plus 1 over S, 1 plus 1 over S, and then we'll have 1 plus 2 over S, and taking this column again, we have this. And this is simply 2, 1. Okay. Then step 2 is to write G hat strictly proper as G hat of S minus T. Because right now you can see that the degree of numerator and denominator are equal. So we have to convert this into a strictly proper transfer function. So we already know what this is and we have computed this. So we need to find out what G hat of S is. Sorry. We already know this and this. Now we have to figure out what is the G hat sub SP. Okay. So this is going to be just 1 second. First one is 2s plus 1 over s plus 1 minus 2. Then we have s plus 2 over s plus 1 minus 1. This becomes 2s plus 2, and then we have 1 over s plus 1. Okay, so now it is in strictly proper form. So minus 1. Okay, so now let's say that we can write this in the form of this in the form of 1 over the denominator function n1 to the power n minus 1 plus n2 to the power n minus 2, so on till just a second. So you can just see that this D is part of the system ABCD, which defines the system in a state space form. So we have found what D is. We have to find out what A, B, and C are. So this is actually C times Si minus B inverse B. So we have to find out what C is. So if that's the case, so if we consider n equals, let's say 1, then we simply have uh, she had this P of S, that's 1 over ds, and then we have question regarding this. Check this 1 second. Mm. All right, so if we just write this down in terms of the denominator function d of s and compare with this, we simply have that ds equals s plus 1. All right, and then this implies that the degree of ds is 1, so we have n equals 1, and we have So G hat SP of S can be given as 1 over ds, which is S plus 1, and minus 1, minus 1. Okay, so if this is the case, then this becomes N1 then. We just need 1 or 1. Therefore, we have N1 over ds. Summarize that equals 1. Okay. So then this N1 implies that we can actually choose C, which is simply just N1, which is minus 1, 1. We have to find out what the matrices A and B are. So let's see that we have some A. Let's write that down in a standard form first. This is minus alpha I equals 3 alpha 1. So these are identity matrices of size k by k minus alpha n by k. We have zeros again and 0. And then we shift this identity matrix to the right, insert 0 here, and then we have zeros through. So actually we have a chain of integrators here. Then this goes on by shifting the identity to the right. And in the last row we have I k plus k, 0 I k plus k. So we have to find out what this k is, right? So the size of this is nk by nk. Okay. So m and k, actually we have 3 indices. We have m, n and k. We just saw that n was the degree of the denominator polynomial ds. And k denote the size of this matrix G hat of S. So for our case, we have a row vector. This is 1 by 2. So for us, m is 1, n is 1, and k is 2. So is the case, then to tell you what these coefficients alphas are. So alphas actually come from the coefficients of this denominator polynomial. So in general, the polynomial example is, let's say, s to the power n plus alpha 1 to the power n minus 1 plus alpha n. For our case, we simply have x plus 1, which implies that alpha 1 is 1. Right. Now we need a matrix A of size nk by nk. For our case, this is 2 by 2. And this is going to look like, so let's see. It should look like minus alpha 1, minus alpha 2, 0 and 1. Okay, so now we have to find out what alpha 1 and alpha 2 are. Just a second. Okay, so these the matrices, the coefficient, the matrices are not always directly related to these coefficients. You have to actually figure out what alpha 1 and alpha 2 are. So, mm, so we have the transfer function. Found out what C is and D. We need to find out what A is. Just 1 second. So before that, let's first figure out what B looks like. B has a simple form. So B is simply ik by k and then zeros throughout. Zeros of size k by k and this other size nk by k. For our case, this is this 1 and k is 2. So we have 2 by 2. Simply identity. 1, 0 and so we have found out what D is, C is, and B is. So we have C and D with us. Now we have to just figure out what these coefficients alpha 1 and alpha 2 are. So let's say that we have this denominator D of S and we have a second order system. So we need at least 2 eigenvalues. So let's say that the eigenvalues are at minus 1 and minus 1. The special equation as S plus 1 squared, which is S squared plus 2S plus 5. Okay. And now we have the matrix A, which is minus alpha 1 minus alpha 2, C1, 1. So the eigenvalues from this, see what the characteristic polynomial is. A minus Si equals 0. And this implies that we have determinant of minus alpha 1 minus S, 1 minus S, and 0. So we have minus alpha S, minus alpha 1 minus S, equals 0. We have alpha 1 plus S. Okay, so now let's expand this. we have minus s square plus s 1 minus alpha 1 plus alpha 1, which implies we have s square plus s alpha 1 minus 1 minus alpha 1. This down and correctly submit. Right? Yes, this has to be 1 0. Okay. Now, if we calculate all of this, then I will just write this down as this 1, and when you calculate this and compare the coefficients with this one whole square, so we compare ES minus 1 0 1 and 0. Okay, so we have the state space realization in which A is this matrix, P is identity. We've already found what B is. C is minus 1 1. Okay, so we have a minimal state space realization for this transfer function matrix. Alright, so I hope that the questions that we did today were clear to you. And yes, so we'll meet again next week. Alright, thank you.